Hey everybody, this is 1.2 polynomial operations, and we're also going to do function notation. So I forgot to update that, but that is what we're going to be talking about today. Last time we talked about polynomials, and now we're going to do stuff with them. We're going to add them together or subtract them and multiply them. All right, so let's do a quick, I guess I don't know if you've done this before, but we're going to add and subtract polynomials. If we're subtracting, we need to make sure we use the distributive property. So let's start at this example. We have this negative, we can call it a -1 if you want, but we're going to need to distribute that before we try and combine like terms. All right, so if we distribute, we end up getting -p, and then over here we end up getting a positive p squared. What's on the right side? We don't really even need that parenthesis. You only need parentheses if you have something in front of it that is like needs to be multiplied by. So we can just rewrite these without that parenthesis. And now we just need to combine like terms. So again, I'd suggest doing the highest exponents first. So 8p squareds, and we're going to add one more p squared, and that should give us 9p squared. And then here we have our p's. -7p, and then we're going to take away one more, so that'd be -8. And we're good to go. Okay, so make sure we put it in standard form. That's what we have right there. All right, let's do a couple more together, and you can practice. How about I do a +1, and then you do b and c. We'll do d together. All right, so this one's a little bigger. This is like a trinomial, and we're going to add it to a binomial. Again, we don't really need this parenthesis because we're not multiplying it by anything. And here as well, this is like +1. If you multiply anything by 1, that doesn't really matter. So the parentheses here don't really apply. I think it's just for grouping to like say we're adding a trinomial and a binomial. All right, now we combine like terms. Start with your highest first. So we have -8x squareds, and we're going to add 7x squared. So that should end up giving us a -1x squareds. Sorry, did I say squareds to the fourth? Next we have our to the thirds, power of 3, and that's by itself. And then we don't have any squareds or just plain old x's. But we do have our constants, and we'll add those together. So 6 plus 5 gives us 11. So that would be our answer in standard form. Okay, why don't you give B and C a try? Okay, so hopefully you gave that a try. This would end up giving us a -6 and a +8 m squared. And then here we have a 5 minus 3m squared. Find like terms. Boop, boop. 8 minus 3 is 5m squareds. And then here we have our constants. That looks like it gives us a -1. All right, and then here again, addition. We don't need those parentheses because there's nothing to multiply them by. Combine like terms. It looks like we get 4n. And then a -4. Okay, so that's not too bad, I hope. Multiplying polynomials. Okay, this is just the distributive property twice. So we covered that last time, and you've done that before. It's just like an extra kind of, we have to do it twice. Just remember when we are multiplying variables, we end up getting a squared. So a times a is a squared. That's what exponents are telling us. That's how many times we're multiplying a by itself, which is different than when we add variables. If we add variables, when we get something like 2a. And that's what coefficients tell us, is that how many times we're adding the variable. So this is when we add, how many times we add, number of times we add, and this is like the number of times we multiply. I can write that. That does not look well. All right, so anyways, if we want to do a squared times a, well, again, we have 2 a's, and we're going to multiply it by another a. We end up getting a to the third. Okay. Or if we had another example, this would be our coefficients. We multiply those like normal. And then here we have 3 a's that are being multiplied, and then we have 2 more a's. Okay. So then we end up getting a to the 5th. Anyways, but what really we're going to doing a lot with is just, a times a or x times x, just like this. Okay, so if we want to do this, we're going to use the distributive property. We're going to distribute 3x to 2x, so that should give us 6x squared. So again, we multiply the coefficients like normal, and then the constants, x times x is x squared. Basically, we add their exponents. All right, and then we'll do 3x times 6. So this 3 times 6 is 18. And then we just have an x by itself. Here we got 12x. And then 36. And then all we'll need to do is combine like terms. We end up getting 6x squared plus 30x plus 36. Okay. Why don't we give this one a try as well? Sometimes people like to do what's called like a box method, and that's just fine too. I'll do an example of that. If you don't like it, then just go the other way, keep it that way. So we just write them on, since we have a binomial times a binomial, we need a 2 by 2 box. Include the signs that go with them, and then we just use a multiplication table. So like 3v times 2v, that gives you 6v squared, and 3v times negative 4 gives us negative 12v, negative 1 times negative 2v, negative 2v, and then negative 1 times negative 4 gives us a positive 4. And then all you need to do then is just add all of those boxes together. So this is a like term. Maybe I'll use a different color. So we have our v squareds, and then here we have our v's. So negative 12 minus 2 gives us negative 14v, and then we have our constant. So that's just one way you can do it. It's one way, like a way to organize your work if you prefer to do it that way. All right, you can even do a binomial times a trinomial. Again, if you want to do it this way, you just need to make sure you multiply everything, you distribute everything to everything. Or if you prefer, you could do like a 3 by 2 box. And sometimes I think that is very useful. As these get bigger, there's more likely that you could make a mistake. So I would just multiply these things together. 21, again, m times m squared gives us m to the 3rd. We add their exponents. Right? We have negative 15m squared, 6m, negative 14m squared, 10m, and negative 4. And we will combine like terms. So we have, and it's always like this diagonal kind of thing if you're multiplying things that are in standard form. Anyway, so we get 21m to the 3rd. We'll combine these two. Looks like we get negative 29. Here we get 16 and negative 4. All right? Okay, so that's what you do if you have to do a binomial times a trinomial, and there will be something like that on your homework or on your test. Last but not least for this is when we have something squared. This is a binomial squared. And all you really need to do here is we need to write it twice. Because that's what exponents are telling us, right? We just talked about that. We just said that like x squared is the same as x times x. So if we have 2x minus 3 squared, we just need to write it twice. And then we can use the distributive property. This is not the same as like just squaring that and squaring that. That would not give you the same answer. You could give that a try and see what you end up getting. Okay, so we're distributing everything to everything. combine like terms. And we're done. Okay? So please keep that in mind. There may be something like that on your homework or test. All right, function notation. So this is kind of, I think, if I recall, you have done stuff like this before, but perhaps you've never done function notation. So you've been talking about functions a lot. Perhaps you've been writing them something looking like that, like y equals mx plus b. When we talk about function notation, it looks a little different, okay? Oh yeah, I missed this. Okay, so a function is like a one-to-one relationship. If you put something into an equation and it gives you one output, that is a function. A better way to kind of think about that is if you draw a function, an equation, a graph, or something like this. These are functions. And I know you've talked about the vertical line test. So if you do a vertical line anywhere on this graph and it only crosses once, then it is a function. Okay? So these are examples of functions. Okay? A non-example, or not a function, could be something like a circle equation, and how that's written is x squared plus y squared equals like the radius. So is an example. Anyways, we won't be doing that for now. If we get to it this year, we will talk about circle equations. But this would not be a function. If you did the vertical line test, it would cross this twice, and so it's not a function. So that's what a function is and what it looks like. If we talk about functions in kind of like in terms of an equation, this is what an equation looks like. Its function, if you wanted to write it as a function, would be something like this. Okay? And when we say this, the wording on how we say this is f of x is like equal to 2x minus 5, something like that. So this wording here, we say it f of x, all right? So you may say, why do we even do that? Okay, well, let's do one more example too. So here we have y is equal to 3x minus 7, and find y when x is equal to negative 5. So one thing that's really nice about function notation is that we can just write that whole thing like this. Okay, they're asking us to, or I guess maybe I should try it like this. Sorry, give me a chance. So f of x equals 3x minus 7. Find f of negative 5. Okay? So this is more like what you would find. And it's not as wordy. And what they're asking us to do is evaluate this function when x is 5. When we talk about function notation, this is just telling us what our variable is. So when we end up doing a problem like this, how we would do it is we would say f of negative 5 is equal to 3 times negative 5 minus 7. So all we're doing is substitution. All we're doing is we're substituting that negative 5 in for what x is. Okay? So how do they relate? How does y and f of x relate to each other? Well, they're exactly the same. It's just a different way to kind of explain it or to use it, okay? We can evaluate functions, and I already did that already, but we'll do another example. So we want to evaluate this function, f of x, when x is equal to 2. So f of 2 would be 3 times 2 minus 7. And then we just want to simplify it. So that would be 6 minus 7 is equal to negative 1. And that would be it. Okay, so it's just asking us to substitute 2 into that equation. Okay, I hope I can finish this before the power goes off. Okay, so here we can do another one. So f of negative 1. So again, we're just substituting negative 1 in for x. So 3 times negative 1, minus 7. So we get negative 3 minus minus 7, which gives us negative 10. So not too bad, all right? So at the beginning of the lesson, we talked about polynomial operations, adding, subtracting, okay? But we are now going to do the exact same thing, but using function notations. Okay, so this is function notation, like f plus g of x. That's how we would say that. But what is that? What does that really mean? Well, what we're doing here is we're doing f of x plus g of x. Okay, so an explanation for this using these values, well, f of x is 3x, and we're going to add it to g of x, which is 2x plus 1. And I would typically, whenever you substitute something in, put those in a parenthesis, just like we did, I guess like right here, where they were in parentheses. Whether or not you will need them, I think it's good to kind of keep those grouped. So now we got f minus g of x. Well, that's the same as f of x minus g of x. So these are equal. And we can do the same sort of thing. So we'd do like 3x, because that's what f of x is from up here. And then we're going to subtract g of x, so 2x plus 1. And again, especially when you're subtracting, you need to make sure that you are putting in a parenthesis, because we will need to distribute that first. So that's 3x minus 2x minus 1, and we'd end up getting 1x. Minus 1. All right, I'm going to see if I can plug this in and have it still work okay. It's always give me issues when it's charging. Okay, let's see how this goes. Okay, next we have f times g of x. So that's how we would say it. Again, what we're doing here, so here we have same as f of x times g of x. So 3x times 2x plus 1. And then we'd need to distribute. So 6x squared plus 3x. And then something like this is just saying 3 times g of x. And an example of that would be 3 times 2x plus 1, which ends up giving us 6x plus 3. Okay, so that is function notation. I have a boatload of examples. I will probably make that be a second video